Okay, let's go. So, we're moving into a new part of the syllabus. And the new part of the syllabus is looking at electrical generation. And words that you should associate with generation are induction, in particular. Induction is important when talking about electricity generation. It was Michael Faraday, an English chemist, who was the first person, to say, well, if electricity can be used to produce motion, that is through the motor effect, current conductor in a magnetic field experiences a force. So electrical energy is transformed into kinetic energy, mechanical energy. Faraday was the first person to say, well, why couldn't the opposite be true? Why can't I convert mechanical energy or kinetic energy into electrical energy? And this is a really important thing for your understanding of science. The reversibility of ideas. Yeah? If I add heat to ice, it converts to water. If I add heat to water, it turns into a gas. If I take heat away from a gas, it turns into a liquid. If I take even more heat away, it turns back into a solid. And that process goes up and down. It's got to do with energy. Yeah? The reversibility of ideas. So we did an experiment, you guys did an experiment yesterday. Perform an investigation to model the generation of electric current by moving a magnet coiled in a magnet. Inadvertently, you also did another dot point, but you didn't plan this investigation. But you performed the first investigation to demonstrate the production of an alternating current. You produced an alternating current. Yeah? The current went forward, went back, went forward, and went back. Yeah? Can you open up your syllabus? And can you tick off these?
Oh my God, my syllabus is just getting worse. Look at that. I've lost a spiral. So you're not even looking.
I am hearing.
You don't care.
I do care so much.
Like, she was in a spiral.
Oh no.
My birthday? Yeah. I'm scared.
Like last week. No? Is it coming
Fearing
up?
for my life.
Oh my god. What do you mean?
It's the week after.
When is it?
No, it's next week. It's the
8th of March.
No, it's the week after.
What days?
Guys,
Saturday.
hey girls, open up your series. Tick them off, please. Annika?
Yeah.
Where's your series?
I didn't wait for you to start to read it.
Bring it to, how many times now? Bring it to class.
Yeah, I'm disappointed.
I
still love you, Annika. Yeah, do we?
You're in the wrong copy. You're in the IDs,
Oh, I found it.
Are you
doing
the
screen recording for?
So the second part of the syllabus.
It's in the third. For one of them is. Okay, so it's on the first and number 2.
Oh, sorry. Second part of the syllabus is, okay, so in the second part of the syllabus, you've done the following. Stop. Perform an investigation to model the generation of electric current by moving a magnet in a coil or coiled in a magnet. You've also, in a way, outlined Michael Faraday's discovery of the generation of electric current by moving a magnet. Now, can you put half there? Because this was one of Faraday's experiments. The other one of Faraday's experiments, you're going to investigate in your third assessment task, which is a practical assessment task. You're going to do an experiment, which may or may not be similar to the one that was in the first half of the video that we did yesterday. And you're going to have to explain what you do and what you see.
Oh, it's scary.
So,
Will it be in here?
now, no, it'll be in that anything else.
In the new lab?
Then, in the third part of the syllabus, you'll see in the last
That's so fun.
dot point, it says plan, choose equipment or resource from the first investigation to demonstrate production of an alternating current. So this is what you did. You took a solenoid. Did it take, how long did it take you?
Wait,
work out. Yeah, to work out how to create the electricity.
What?
Oh no, sorry, I told you how to do it. Sorry, yeah. So, if I wasn't here, I would have given you to. I would have given you. Alright. So, you place the magnet in, and then what happens when you don't move the magnet?
It's zero.
It's zero. Why?
Because kinetic energy is not transferred.
Well, that kinetic energy is needed. In this case, there's no kinetic energy in the magnet. Yeah. When I move the magnet, yeah, I get the creation of electrical energy. Okay. All right. Now, that's what Faraday wanted. He said, why can't I transform kinetic energy and create electrical energy? It's like the opposite of the motor effect. Yeah. It's the opposite. So, we can explain it in terms of energy, but we can do a bit better than that. Okay? We can do a bit better than that. And what Faraday said was that whenever he found this through investigation, any change in the magnetic environment of a coil of wire will cause a voltage to be induced in the coil. So here, when I'm moving this, the wires here are experiencing a changing magnetic field. Yeah? You can imagine if I was to draw the field lines around a magnet, they're not all uniform. That is, they're not all evenly spaced. Yeah? They're not all evenly spaced. And when I move the magnet, the wire experiences a changing magnetic field, or what we'd say a changing flux. And we've done flux, we've done magnetic field, yeah? No matter how the change is produced, the voltage will be generated. For example, I could hold this and I could move the coil, yeah? There's still relative motion, it's important, that idea, there's relative motion between the two. The change could be produced by changing the magnetic field strength. Yeah? I could use, instead of a permanent magnet, I could use an electromagnet. And I could turn up the voltage and hold it still. And as I turned up the voltage, and the magnet will become stronger, and this will experience a change in magnetic field. Yeah, that would work. So long as this experiences a change in magnetic field. I'm moving a magnet towards or away from the coil, moving the coil in and out of the magnetic field. I could rotate the coil relative to the magnet. Yeah? So this equation here is also, it's the equation version of Faraday's law.
What's M?
Magnet. You don't have to say, that's irrelevant. Yeah. I looked for it online forever and I said the first one I found. So, this sign here, epsilon, is EMF, or what's known as electromagnetic force. Okay? Electromagnetic force is another word for voltage. Okay? Electromotive. It's another word. It's, what did I say?
Electromagnetic.
Not, oh, definitely. It's electromotive force. And you can write it like this, EMF equals epsilon equals changing magnetic flux divided by changing time. Okay? Changing magnetic flux divided by changing magnetic time, changing time. Now, for example, here's an applet, yeah, and actually I'll go back to this. Yes, please.
Which one?
Now, we can do a little bit better than this because we know that you guys did this equation yesterday, yeah? This is the same equation. Voltage generated equals, now this is a new symbol inserted into the equation, and it is the number of loops in the coil. Yeah? here, if I had half the number of loops in the coil, what would be the effect, do you think, on the induced voltage? If I halve the numbers of coils, it would halve, yeah. The induced EMF would halve, yeah? So N is a factor. Now, this change in flux is the same as, or is equal to, the magnetic field strength, or the flux density, times the area. We did that worksheet. Do you recall that? Yeah. So that's the same thing. We'll just substitute that in. And then we've got change in time. Where does the negative symbol come in? Well, we'll look at that in a little bit. Okay? But that's important.
Because isn't it travel against or something like that?
We'll have a look. Okay? But what this equation says is this. Increasing the number of coil turns increases the size of the induced EMF. If I have more coil turns here, I'll have a greater induced voltage. And if the circuit is closed, current will flow. That's really important. A lot of students say, changing magnetic flux induces a current. That's wrong. A changing magnetic flux induces a voltage. And if the circuit is closed, the current will flow. Okay? Got to think like that. One step, let's do this, let's do this. Okay?
You can't assume that like it's a closed circuit.
Correct. If I also increase the magnetic field strength, increasing this, I have a stronger magnet, should increase the size of the voltage. If I increase the area of the coil, if this is bigger, well, I like to think of it like this. If this area was 0, then the induced voltage will be 0. Yeah? So let's make the area a little bit bigger. Well, greater voltage induced. Let's make the area even a little bit bigger. Greater voltage induced. Yeah?
Does the area mean like the width?
The area of, like for this, the area would be that.
To the inside?
Yeah, yes, like that. And then lastly, if I move the magnet really fast, and this is really small, yeah, if the change in time is really small, and it's on the denominator, then the voltage is going to be larger. Yeah? So let's just trial one of those things.
Did you post this beautiful presentation on our site?
I can. Let's see, for example, what happens if I decrease the loop area. Okay? If I move the magnet in, I'll try to do it with the same consistency both times. Yeah? Not a really large induced voltage.
Can't really tell.
All right, let's do loops. Let's do number of loops. 3 loops. Oh, well, that's good.
That's bigger, isn't it?
Okay, let's do 1 loop.
Smaller.
What?
Okay, so what I'd like you to do, what we're going to do is this. We're going to do it today. You have to plan, choose equipment or resources for and perform a first-hand investigation to predict and verify the effect on a generated electric current when the distance between the coil and magnet is varied, the strength of the magnet is varied, and the relative motion between the coil and magnet is varied, i.e. change in time. Okay? How are you going to do this? I've got an activity that's ready to go for you on our sites page. And
I love them. It's so fun. Oh, Greenland is swaggy.
No. No, I know.
Because they're not as important as others.
Yes.